there's no atmosphere.
I'm not assuming anything. I'm just saying that you haven't verified. You haven't verified that every time something appears above the horizon, where it should be, according to the predicted curvature, should be obscured. It's because of refraction. But that doesn't make any sense.
As soon as you say the word should, you are making a prediction, and there are assumptions or something behind that prediction. What are your assumptions behind your prediction?
Well, no, it's not an assumption, right? It's not an assumption. From what we know, right? Light bends towards a denser medium, causes things to disappear, right? That's why we get bottom-up obstruction. That's why things...
What? Start again. Light bends towards a denser medium, makes things disappear. How does that work?
No.
So light, when it hits an object and reflects off an object, that light is going to bend towards the denser medium and never get to reach your eye, right? Because it hits the earth. The light rays hit the earth. They get obstructed.
Hang on. I'm cracking out the crayons in paint.
Don't Roohif do that.
I got it.
Now, this has already been demonstrated that there's a downward bias with refraction. You have the crosshairs on a theodolite. When you balance out your total station or whatever device you're using, transit, whatever, it's well known for hundreds of years now that you have basically 4 different types of refraction. So when you have the crosshair set up and balanced, and you line it up with the horizon, above the crosshair you have looming refraction and stooping refraction. And then below the crosshair you have sinking refraction and not stooping, excuse me. Below the horizon you have sinking refraction and stooping refraction. Above the horizon you have looming and towering refraction. And then you can include you got your superior mirage that's also above the crosshair or above the horizon. And you got your inferior mirage that's below the crosshair or the horizon. Now, almost every single time when you look through the theodolite and you level it, the optical horizon, right, the apparent horizon, because you guys call it, you think it's geometric, but the apparent horizon's almost always, 99% of the time, it's below the horizontal of the crosshair. Why? Because of sinking refraction, right? Because of because of the lenses of the theodolite cause the horizon to dip. There's a horizontal dip below eye level. This is well known and established for almost 300 years. Now, anyway. Why is there a bias towards the bottom half of our field of view versus the top half? It's because light bends towards the denser medium. Go ahead.
Right, let's get back to where you said the ray wouldn't reach your eye. I busted out the crayons. All right, so the sun's up here, whatever. Oops, shit. Ah, crap. Hold on.
Please don't be perverted with your drawings, please. It makes me feel like you're peeing on the house.
It's a gay little house. All right, so we've got the sun up here. Cool. And it's shining down onto our gay little house. All right. And what you're saying is that this light ray that bounces off the house and heads towards you is going to hit the ground because it bends towards the denser medium, right?
That is the idea.
Excellent. Okay. What happens to the ray that bounces off at this angle? What happens to that one?
It scatters, but that's why.
Oh, what?
That's why the top of the object, right, is still visible compared to the bottom half. That's why you get. No. That's why you get bottom up obstruction. That's why the obstruction begins at the bottom first, not the top.
The same spot on the roof. It's one ray's bouncing off this way, horizontally. Another ray's bouncing off slightly upwards. Where's that ray going to go?
If you consider both Snell's law and Fermat's principle, depending on the angle of the light, whether it's 25 degrees, 45 degrees, 90 degrees, if it's going to bend at different rates. I can't exactly predict. It depends on the gradient densities. It's kind of complex, bro. But I would expect the light to bend away, right, in a way that it will never reach your eye. Either way, it's called light diffusion, light scattering, attenuation, all of that.
All right. So this one bounced off horizontally, and you're right, it bends down, hits the floor before it reaches my eye. This ray bounces off at a different angle, still bends down, but goes way over the top of my head. What about this ray? What about that one?
Yeah, so it's like I said, it's the light has a natural bias to bend downwards towards a denser medium. Now, this image right here is a very crude representation of what's going on in reality. It's not to scale at all. That house was going to be way farther away, and the way that the light hits that house when you're talking about 20 miles out in the horizon. Yes, the top of the house is going to be the last part to be obstructed, right? Because it's higher. Now, the bottom of the house is going to be completely obstructed. You might only see the tippity top of the roof. And depending on the atmospheric conditions, the greater the refraction, you're not going to see the house at all. That's just a fact. You can take that to the bank. Refraction causes things to be completely obscured. The less refraction, the greater visibility. That's why the Weather Channel, they talk about, today's you have, 3-mile visibility. Why? Because there's less refraction. The more refraction, the less visibility. You disagree with that?
Here we have a mountain.
No. Do you disagree with that?
His understanding of refraction is rubbish. That's what I'll say.
No,
it's not rubbish.
Do you understand what he meant by that?
Say it again briefly.
Let me ask you. With less refraction, it increases visibility. With more refraction, there's less visibility.
When you say visibility, I'm wondering whether you mean scattering or bottom-up obstruction.
All of it combined.
Different.
With less refraction, you have less scattering, you have less diffusion, you have less refraction, all of that. Because when you have gradient densities, when you have atmospheric particulates and dust and pollen and this and that, it's going to cause things to be less visible, bro. It's pretty common sense.
Less resolvable because of scattering? Or more obstructed bottom up? They're different things.
The less refraction, bro, right? The less evaporation. There's going to be greater visibility.
Yes. Also, Roohif, in your image, can you cut that mountain out and tilt it 1 degree away, please?
Okay.
Thank you. Or maybe 2 degrees.
Okay.
What do you mean by the bottom up?
Who, me?
Oops. There you go. Just pretend that's 2 degrees.
No, Roohif, no. What do you mean by the bottom up scattering?
He's saying with the less refraction, causes both scattering or less scattering and less bottom up obstruction. They're different effects for different reasons.
Now I'll give you this. I'll give you this, right? There's rare instances where refraction can cause something known as a superior mirage or fata morgana, or looming, right? Where things appear way higher than they should. Boats float, you can see things but that's very rare. That's very, very rare. And that's the exception, right?
Yeah, but
that's
it's
the
not
exception.
Refraction either.
Hold on. I don't know. It's considered reflection. Regardless, you can catch me in a technicality. You know what I'm saying, bro. So now to dwell on the exception when we know that there's a downward bias and 90% of the time things dip below the horizon because of refraction, to say that refraction is causing things to appear above the horizon is foolish, bro.
Okay, bro. Anyway, where were we? This was the mountain. So we've got the sun hitting.
What refraction are we dealing with? We're here, Roohif, by the way, so we know. Are we doing terrestrial refraction? Is that what we're focusing on here?
Yes, we're on the Earth. We're not looking at
Yeah.
things in space.
Okay.
Well, I
Now,
think
you just said earlier with what? Less refraction, right? Less refraction. I should have less obstruction, though, correct?
No, more refraction if you have a steeper gradient. So when he says less refraction, that means to me a gentle gradient. So less refraction means you have more obstruction bottom up.
Are you tripping?
No, I'm not.
He's coping hard right now. He's coping hard, dude.
Well, listen. If there's a clear day, let's just talk about a nice clear day, hardly any refraction out there. You're gonna tell me I'm gonna have
can't
more
say-
obstruction?
You can't equate a clear day with less refraction. Those two things are
I
not
just
related.
said both. I'm giving you both. No, Roohif, I'm giving you both. Don't do
Okay,
it to me.
clear
You know what
day.
you're doing here.
A clear day with less refraction, yeah, you'll have more bottom up obstruction.
Hardly any refraction. Hardly any.
Yeah, the less refraction you have, the more bottom up
Mhm.
obstruction you'll have.
Wow. This
So
is why
what-
refraction
what-
needs to be
so-
done again.
What
Go ahead.
would you expect? What would you expect in a vacuum? Theoretically,
No.
if the Earth had no atmosphere, what would you expect then?
Yeah, we'd see the geometric horizon all the time. That would be the horizon.
I just think you're messing with.
Hang on, I've got a GeoGebra that I think is probably going to be easier.
could I ask Lion a question real fast?
Yeah, go ahead.
Chuck Missler, I looked it up. He had originally postulated that the Bible proves like a round Earth, but now he's got documents on Pinonia House, his website, that are very extensive that talk about the holographic universe and how it supports the flat Earth, which is
Yeah,
I
he's a
just
ma-
finished.
I haven't
Thank
kept
you.
up with him. He's still alive, Chuck Missler.
I'm not sure actually. I thought he passed away.
They all.
Great
I think Michael
mathematician.
Heiser passed. I think they all passed away. Rob Skiba passed. They all passed away, dude. It's nuts, dude. Chuck Missler, Michael Heiser, Rob Skiba, dead.
Yeah, like 2018 was when I think it was like 2015 or 18 or 20. So it was recent that Missler died.
Yeah, Chuck, he was taking on evolution and trying to debunk it using math.
Yeah, his
There
content's
we go.
going
All right,
low-key
ready?
viral right now.
Are we
Yeah,
ready?
I'm ready. I'm watching. I'm looking. Don't worry. I'm looking.
Cool. So I'll make that really tight. All right, so I've got two sliders. One is the observer height in meters, and this other one, the light radius. Right. So if the light radius is small, so small being 8,000 here, this is the radius of curvature of the light. Right. How much the light curves. A smaller radius means that it's curving a lot, and a big radius means it's going pretty straight. All right. So that yellow line. Right. Does that make sense? Big radius, relatively straight. Little radius, curving a lot. Cool?
Mm-hmm. Yeah, I'm
All right.
looking. It's a little small,
All right.
but I can see it.
Okay, I'll try and zoom in. So this is, that's probably Kanigu actually, that one. Let's move in. Let's just do the horizon first.
Why is it not tilting away?
Did I make it tilt? I don't know if I did. Maybe I did actually. I think I did. Look, yeah, I think I did.
Okay, thank you.
Tilting, yeah, it's tilting away like 2 degrees, which is nothing, right? So
This is why you guys try to win all the time, though. You know, when we see things, you're just like, refraction! Too much refraction!
you can
It's
hold
like
us
you guys have
to-
used it against us. You guys have claimed refraction, took it, and try to own it for your, like, winning battle game.
Right, this light radius here, this is approximately standard refraction. It's about 44,000 Ks.
Even though you guys have only studied it for like 200 meters, right? But you know that far?
Right.
Interesting.
No, I think you brought that up before, and I asked you to send me what
Yeah,
you were
and
talking
it's
about.
also been talked about. Have you looked into it yourself? Because I've already talked to professors. Roohif, have you know anything about refraction, how long it's been studied, and how far? In a lab or anywhere, any source? How far?
Yes.
How
People,
far?
they do it over hundreds of kilometers when they do trigonometric hiding.
Okay, show me a test where they're doing over 100 kilometers and there's proof of refraction in this way. Then show me one test.
Okay, it's in the
Ready, please?
American Arc of the Parallel. I haven't got it to hand, but it's in the Arc of the Parallel. They do reciprocal angles to get heights of mountains. And they have to, yeah,
I'm not asking for you to do a measure. I'm asking studying refraction. And also in a lab source, figuring it out because they're quantifying it after 200 meters. Do you understand that?
yes, I have never seen a limit of 200 meters to refraction. So anyway.
Now, there's not a limit. It's only been studied at 200, and after 200, it's quantified for your little d in mathematics.
All right. Anyway, so this is the observers at 500 meters.
Exactly.
And,
avoid it.
well, I'm sharing so that I can explain this. All right.
I understand.
Refraction lets you see further. So this is less refraction. This is standard refraction. And you'll see that the red dotted line hits the globe Earth at G. That's the geometric horizon. But the yellow line is the actual curved path of light. And it hits a little bit further. So this is where the horizon is. All right. So here it's about 80 Ks and here is about 86 Ks. All right. If I turn up refraction, make it stronger, so the light bends more, guess what happens to the refracted horizon? It gets further and further away. All right, so we can see more around the bend with stronger refraction. And so this is Canigou. So with Canigou, I think, yeah, Canigou is meant to be, hang on, they're 300 meters at Canigou, aren't they? So I'll set the observer about 310 or 320, I think. One of those. That's that. All right. So it's close to no refraction. With the red line is no refraction, straight line of sight, misses the top of Canigou. But if you have standard refraction, about 44,000, you see the very tippy tops of it. Cool. That's what we see.
I don't know, dude. That seems like there's too much fuckery.
Dude, this is literally a 2-scale representation of the Canigou observation.
To me, it feels mostly theoretical. It hasn't really been substantiated. But I get it works out on paper,
Yeah.
but I'm not entirely sure that's what's going on in reality. Because
Okay.
you're asserting that
Good job,
refraction
Ryan.
makes things appear. I don't know that to be the fact yet. I don't.
Well, look at the path of light. Light's this way. The light's curving from this part of the mountain, curves into the observer.
Roohif, do you remember the index number for refraction that was used for that time? And do you remember the temperature?
No. Don't make me bring up the graphs. Once you get above the surface, the typical gradient, the refractive index changes from whatever the height is per vertical kilometer, changes by 0.000023 ish.
How do you know it changes by that and only that standard?
Because I have
over
the
that
data.
mile? Wait. But you actually have the data that they went out there and they asked you, or is that just figured out that they say that's what it should be that day? Do you actually know at every mile, 2 miles, 3 miles, it's actually changing and you're using the correct refraction?
No.
Do you know?
Every single weather station, once you get above the surface, clusters around that value. That's why we use that value.
I understand. You guys use a value. There's an actual standard value. But in reality, is that happening in your atmosphere for a fact? Do you know that after every single mile?
Yeah. All the data
you know
says
that
so,
for a fact.
yes.
That's the biggest lie I've ever heard from anyone on here at Roohif, because I've heard Globers even say that there is probably a change, and they cannot stay with standard refraction. That they agree that yes, it needs to be revisited because over 100 miles, especially using standard refraction, you would not know. It's going to change. You're using just because, it's going to change this much in a mile. It's going to change this much in a mile. But you don't even know what's going on out there. You're just using the same fucking refraction every day. Oh, it's about this out there. This is going on out there.
So, why is it that when you look through a theodolite, that the horizons always appears below eye level?
Stacy asked for the graphs. Hold on.
Oh, goodness gracious.
Here we go. What's this one? This one is
you focus on the wrong things of discussion.
Boise, Idaho. This one is Denver. This one is Santa Teresa, New Mexico. This one is Key West in Florida. What else have we got? This one is Lamont in...
It doesn't matter though, because that's all in reference to the predicted curvature of the Earth already.
No,
So
it's not. No, it's not. You keep
how
saying
do we
wrong
know that?
things.
How do we know
Because
that?
these are vertical measurements. They just send a balloon up. Nothing to do with the curvature of the Earth.
Vertical measurements of refraction.
Yes.
How do they measure that?
They measure the
They just-
temperature,
a
pressure,
laser or
humidity, and
something?
the altitude. No. Temperature, pressure, humidity, and altitude.
Yeah, but how do they measure it though? The refractive index. They just get it.
Yeah,
Those
those are inputs. Those are inputs into an empirically derived formula to give you the refractive index.
So
This is a formula, hon.
they gather the temperature, humidity, the pressure, all of that, and they put it into what, an AI, some
No, into a
algorithm, and
formula.
it poops out some formula for standard refraction. Like I don't
No,
understand.
into a formula that was derived from laboratory experiments.
I've only so many meters. This is what I keep saying. And then they're quantifying everything
Oh,
after that because the atmosphere does this over 100 and some odd miles.
Yeah,
They
look at
say
the
this
shape of all
happens
the
every
graphs.
single time I use the same refraction on every single day, depending on what the temperature is in that certain area. Then every single mile after that, they keep doing it, quantifying. This is
Right, look at the
absolute
graph.
bullshit. This is my refraction is crap.
Do all the graphs have a similar shape?
Oh, for fuck's sake. Roohif, I'm not doing it with you about the grass.
Well, this is the data. This is the data.
So,
You know what you're
It's on
doing,
the
Roohif,
surface.
Roohif, what's the standard refraction index at room temperature? Do you know the
standard
approximate?
gradient? The standard gradient, the refractive index changes by 0.4 zeros, about 2.3. 4 zeros, 2.3 per kilometer.
Why is it
Vertical
that
kilometer.
when you
What do you
guys
mean,
do
why is it?
when you guys do theodolite measurements, that it's recommended to do it at least above the what's it called, the marine layer,
Yep. Get above the
right?
surface, yes.
How much higher above the surface would you recommend?
My data says about 100 meters is pretty safe.
100 meters is pretty safe, but the higher you go, it becomes better, right? Like theoretically, if you're in a mountaintop, like let's say you're 11,000 feet up in Afghanistan,
Yep.
why is it better up there?
It's the gradient is much more stable when you're well away from the surface.
Yeah, there's less refraction, right?
No, not less refraction. Right?
Oh,
It's more
here we go.
stable.
Can you at least admit one thing? Because I asked you about a lab. I asked you about quantification. Now, can we at least go to standard refraction, like I just asked you earlier? You told Lion they go from a lab, right? And then everything after that is going to be quantified. Isn't that correct?
Is it quantified?
Yeah, for
Predicted?
your math. You did a test in a lab for how many meters?
No.
This is what refraction's using. How many meters?
Yeah, probably 30 centimeters. That tiny little piece of equipment
Okay,
that measures
so
the
we're
refractive
talking about the refraction that y'all keep using every day. How many meters then it's quantified, please?
index. As in over what distance was the refractive index determined in the lab?
Correct. This is what you
Yeah,
guys keep
30
using every day when you claim
probably 30
refraction. So I
centimeters.
want to know
Yeah.
when you're using it and you came up with it, how many meters and then quantified, please.
Yeah, probably 30 centimeters. They're tiny little things. They've got a vacuum in one path.
There.
And
So
the
everything that you
sample
guys keep using every day, about 100 fucking miles, is from how many diameters, honey? In a lab.
in a lab to determine the refractive index of
You're
air.
welcome, everybody.
with
Have a nice
particular-
day. Don't need to speak to Professor anymore, do you, Roohif?
To determine the refractive index of air with those characteristics. That's all they did. So it's so that I know that if the temperature's 20 and the humidity is 50% and the pressure's this, I know what the refractive index is. And then I apply that to these measurements of the atmosphere, which tell me that
I'm glad that we
that I
got on
can
the same
apply.
page. We don't need to go ask a professor now. I've already done my work. I've already done it on the streets. And I've already talked to them. Your standard refraction that you kept denying, would not admit, is from a damn lab that you quantify. And then you want to go 37 meters to 100 and some odd damn miles. Roohif, this is where you guys go wrong.
Jesus.
Now I'm going to
No,
go outside and have a
this is where you're
cigarette.
not
And thank
understanding.
you for admitting finally that you know about the lab and you know how many meters that you guys are quantifying. Have a nice day with your dumbass refraction, Roohif.
Okay. Thank you, Stacey. I love
Hold
you
on.
too.
I think I understand where the misunderstanding is.
Yeah. Have a go. Yeah.
What's understood in a lab is the refractive index. Standard refraction is done in the field.
Incorrect.
Have I got that
Actually
wrong?
correct. So
Yeah. Okay.
have I given you this lecture, manufactured item? I may have. So basically, there's a I'll stick the paper in the chat. One sec. I'll stick it in the chat after I stick it in your mom. All right, paper's in the chat, and that's the paper that an Aussie guy did actually, and he took a whole bunch of empirical lab experiments, and all those experiments came up with formulas for the refractive index of air under certain conditions, and he made them super accurate. So the refractive index is usually given to about 6 decimal places. This guy got it, gave the accuracy to about 8 decimal places, which is pretty cool. Anyway, so that's the basis. So this paper basically gives you a formula. If you plug in the wavelength, temperature, pressure, humidity, CO2, blah blah blah, you get a refractive index, right? And those graphs that I kept showing are from weather balloon data, where they don't calculate the refractive index. They just get the temperature, pressure, humidity, altitude, blah, 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 right? So I take that data, and for each sample that the balloon takes, it's like, oh, here's the sample at 100 meters. I calculate the refractive index at that 100-meter height. Then the next sample might be at 200 meters, and I calculate the refractive index there. So I've got a change in refractive index over that 100 meters, and I just normalize that to a kilometer and stick a dot on the graph. So that's what those graphs are. Does that make sense?
All right. What about when things are obstructed way sooner than they're supposed to be? What do you
What
call
are those?
that?
Like such as
Yeah, like the bridge near Rakia's crib.
the bridge or his
I forget that bridge's name.
trawling boat, the trawler.
You go the one that you can take a photo from the left and it looks like
Pontchartrain.
it's curving left. Yes. And if you take a photo from the
Pontchartrain,
right, it
sorry.
looks like it's curving right, but really the bridge is curving left or right. And at times it's like the Earth is freaking blocking it way sooner than predicted.
I've seen a few inferior mirages on Pontchartrain, but do you have one without an inferior mirage?
Or any observation where things are obscured sooner than predicted, than the radius of the Earth predicts.
Yeah. The only
What's
one I can
causing
think
that?
of with Rakia's got a fishing trawler that he claims was, I think, 5-6 miles away. Rakia has apparently, not while I was there, but apparently acknowledged that there was quite the swell on that day. So, yeah, and that the boat was bobbing up and down. That's the only one I can think of. Have another one? Please present it. Oh, it's time. 8:50. Holy shit! I haven't fed dogs yet. I'm going to do that in 10 minutes. Did you follow the explanation? MFT. Motherfucking totem.
Yeah, I got it.
Yeah, I've been giving this lecture to Flurfs for probably 6-7 years, I think.
Yeah, I've been trying to explain refraction and how light curves for a while. I don't know if it's. I don't know. Ultimately, it's, as far as I can tell, it's one of two things. It's either special pleading where we understand how light works, we understand refractive indexes, but somehow, for some reason, they just break down at distance. Or I don't know if it's an appeal to possibility exactly, but whatever it is, there's something in the atmosphere doing something that transforms all of these globe observations to
There's
black.
some special particulate matter that just makes Snell's law go in reverse or something. Yeah, I've heard that before as well.
Yeah.
Cracking
But the main
stuff,
thing,
people.
what gets me, like, when you talk about celestial navigation and the angles to Polaris, the amount of refraction you would need for that is something on the order of like 25 to 30 degrees.
Yeah.
But something like 6 arc seconds at the Black Swan is apparently too much refraction. It's like a panacea.
Oh, it's a couple of minutes, isn't it, for Black Swan? I think.
I think I don't
Who
know.
was
I
saying-
calculated for like 9 arc seconds. I think Scott Mackey said 4. Don't know.
Hang on. Someone said before the horizon being below eye level due to refraction. That's rubbish. Due to the Earth being a globe. Check the chat.
Well, I have quotes from the Royal Astronomical Society in the 1800s testing the horizon at sea level. We're talking about 6 inches above the water, at 20 feet, at 50 feet, at 100 feet, at 150 feet. Many observations were done, and even 2 miles up in a weather balloon, or not a weather balloon, a hot air balloon. In the basket, they set up an experiment. At every single instance, they had a theodolite with glass, and then they had basically a steel tube, a steel pipe that was closed at one end with a small aperture right in the center, and then on the other end it was open with a crosshair. And they compared the observations through the theodolite and then through the steel pipe, and they noticed that at every instance, including at sea level, the horizon dipped below eye level through the theodolite, through the glass of the theodolite. Now they figured that because of the glass of the theodolite, there was some type of refraction occurring. They called it calibration. That made the horizon always appear below the horizontal line on the crosshair. Now in modern times, they know about this and they correct for that. Even in the manufacturing of the theodolite, they try to correct for that. And there's also calculations.
Horseshit.
It's not, dude. I can do that. Dude, I have books that talk about precision manufacturing of optics, including telescopes, theodolites, and cameras, all of that. And this is something that is well known in precision optics that they have to account for. It's called collimation. Because light bends downwards. What?
Do you want to hear why it's horseshit?
Why is it?
Because you can flip a theodolite. You turn the theodolite upside down to make a second measurement, and the horizon's still below horizontal.
It doesn't matter the orientation of the theodolite. It has nothing to do with the orientation of the theodolite.
So it's nothing to do with the theodolite or the optics.
No, the light always bends downward. It doesn't matter if you hold the theodolite backwards. It has nothing to do with it.
Yeah, you just said they made things for the
optics.
optics.
It doesn't matter the thickness of the lens. Whether it's not, is the thickness going to change when you turn it upside down?
No, you're looking through the center of a circular
lens. Right. So why would it matter if you flipped it upside down?
It doesn't. You're the one that claiming they had to do corrections for the lenses or some shit.
No, the thickness of the lens causes the light to bend down, dude. Literally, it doesn't matter how you orientate the lens.
The crosshairs are in the center of basically a spherical lens. Right? There's no distortion through the center. That's why the crosshairs are in the center.
No, there's still a horizontal dip, dude.
I agree.
Now, if you want me, I'll pull up. Dude, they're globers. These are globers that are observing this. This is well documented.
The horizon is below horizontal. Yes, nothing to do with the optics.
No, it is the optics. How do they know? Because they used the steel pipe with no lenses. Just a regular steel pipe with an aperture on one side and a cross on the other, and they did the same exact measurements. They had both It was perfectly leveled, just like the theodolite was perfectly leveled. Yet every single time they looked through the theodolite at every elevation, the horizon was always below eye level.
Yes,
Below the
and nothing to do with the theodolite. Right.
theodolite. Now when they look through the steel scope with no lens, the horizon was always at eye level, always with the horizontal line on the crosshair.
Show me that.
Even at 2 miles up in a hot air balloon.
How do you level a theodolite in a fucking air balloon?
Listen, they did it. It's documented.
I would love to
Look,
see how.
I got the names of the scientists. It's the Royal Astronomical Society from the 1800s.
Yep.
Now, with that being said, even in geodesic measurements, they account for this. This is well known, bro. And they correct for this in the calculations, just like you have standard refraction. They correct for it. Now, when
refraction, yes.
they're correct for the horizontal dip. That's why for example, when it comes, you brought up
surveyors. Surveyors don't.
Hold on, dude.
Point at the horizon, dude. Surveyors never point at the horizon.
I'm not talking about that.
I've got to interrupt when you just talk absolute.
I'm not talking about that. I'm talking about collimation. Look up collimation, bro. Yes. So to correct for collimation, what they do is they have the stations point at each other, and they act like that's gonna cancel it out. That cancels out any collimation error. Go look at it. If you don't,
do a two-peg test.
I know what I'm talking about, dude.
No, you don't. You clearly don't. To fix the collimation of a theodolite or an auto level, you do a two-peg test. Would you like to see a video of me doing a two-peg test?
Oh, so now you know what I'm talking about all of a sudden.
Yeah, because I know that you're full of shit.
Right. So 2 minutes ago, what are you talking about? There's no collimation. Now there's collimation. That you have to correct for.
Is an error that you can adjust out of an instrument.
No shit. That's what I'm telling you, dude. And you're ignoring it. You're acting like that. What are you talking about?
So you're talking about people just using an uncalibrated instrument. Who gives a shit?
Exactly. So you have to calibrate, as in, i.e., you have to correct for an error that's known as collimation that's caused by the lens of the theodolite.
It's caused by your theodolite being out of collimation, I guess, out of alignment. There's no downward bias.
So they have to correct for that. They have to realign the horizon.
Calibrate, not the horizon. Not the horizon.
No, I know. But you can notice this collimation error. You can notice it by using the horizon as a reference.
No.
Now, granted, they don't use the horizon when doing reciprocal zenith angles. I understand that. That's not the point here. The point is you can notice this collimation error when you level out your instrument and then you reference the horizon with another instrument that doesn't have any lenses. You can see this error manifest.
Surveyors never reference the horizon. That's just rubbish.
I didn't say. I know that. I just told you that. I granted you that. I'm not talking about that. I'm saying in order to notice this error, though, you can use the horizon as a reference to notice this error.
You can't do that.
You don't use the horizon for spherical axis or reciprocal zenith angle.
How do you compare it to a horizon? Like, what if it's a strong refraction day? Then you've just adjusted out a collimation error that isn't there. It's retarded.
Now, here I can't pull it up right now, but I got manuals. I got a manual on precision optics and the manufacturing of precision optics. It talks all about this stuff, dude.
Right.
And when you talk about lenses and like barrel distortion and chromatic aberration and all this and that, collimation is just one of many things that lenses cause light to distort, right? You agree with that?
If you're looking through the center of a circular lens, then no, it's not going to do that. What's your username now? Lion. All right.
Can you find the original 1800 thing?
Yeah, hold on. Give me a second.
I remember reading that.
Right. There's a video of me calibrating an auto level using a two-peg test. All right, I'll get out feed doggies. It's 9:00. See you soon.
Yeah, I remember you posting that 1800 thing, and I remember reading it and it not saying what you're saying it says. I mean, I don't remember off the top of my head, but I remember there being issues with that.
And they even said that it looked concave, dude. The horizon, at some point, the higher you go, it looks like it's curving up. But it's not actually curving up. It's all due to, distortion. Like the edges looked like they were curving up. The point is that for whatever reason, though, there tends to be a downward bias when it comes to the axis of the theodolite, the crosshairs. Almost always, you'll notice things below horizon. And you guys say, well, that's because of the curvature of the Earth.
Yeah, the curving up wouldn't affect what the crosshairs are in reference to. The light's doing whatever it's doing before it ever gets to the theodolite. Like, it's not going to bend the light out in the distance.
No, I agree. So it takes extreme refraction to cause things to appear below the horizon, right? You guys act like extreme refraction causes things to manifest or appear above the horizon. That's not the case, dude. The more refraction there is, it acts as if the globe is way smaller, dude. As if the curvature is way higher than the expected 8 miles per meter squared. Per mile squared. No, that's what happens. The more refraction, the more atmospheric density, the more water vapor, evaporation, heat, it causes things to literally completely be obscured. You guys act like, no, that causes things to pop up.
Yeah, that's just not how it is. Something. So what Roohif was trying to illustrate with that the house and the little guy. You understand that when light bends down, our eyes presume that light is going straight always. So if we get light bending down to our eyes, it projects the location of that object upwards, right? Like light bending down lifts the apparent image.
Yeah, I know you guys assert that. And that on paper it might sound good, and you might have standard refraction.
Sound good.
But that's the thing is the whole thing with standard refraction, it's affirming the consequence, bro. The whole reason you came up with standard refraction, and this is admitted in the geodesic manuals, you guys assume the predicted radius. So when you come up with standard refraction, you make it line up with the predicted radius. That's what standard refraction makes it line up with the predicted radius. It has never been demonstrated to be the case.
It has been. So you could say that we assume it today, but that's because we figured it out a long time ago. And regardless of whether it's affirming the consequent, as you say, which it's not, but whatever, it doesn't change the fact that it's just geometry. It doesn't look good on paper. That's just how it has to work. And it's not just because of standard refraction, it's just light in general. If light bends downwards, it lifts the apparent image. You can do this with lenses. Not just the atmosphere. That's just how light works. It's not going to work differently because we're talking about the atmosphere.
If an object is looming higher than what's predicted by the radius, or is obstructed sooner than what's predicted by the radius, you come up with a refractive index to correct for that, and then you basically reverse engineer and affirm the consequence.
What's the difference to you between a reason and an excuse?
Deadline.
What's the difference between a reason and an excuse? What do you mean?
Because it sounds like you're saying these are all just a bunch of excuses, right? But if that's actually what's happening, right, if we're right about this, then they're not excuses, they're reasons for why we see what we see. So I'm asking, what's the difference to you between something being a reason something happens and just an excuse?
Well, you can have a hypothesis, right? A reasonable conclusion to why something is occurring. And then you can correct for that hypothetically, which is what you guys have done, but you haven't actually demonstrated that through experiments. You have not. Nobody's done that. You say, "Oh, well, we did it in the lab." Dude, the lab is not. You can't do what you can't do that in the lab.
Absolutely, you can.
How?
Yeah, you can do it better in the lab because you can control for various factors. If you say that there's some hidden variable out there that we haven't accounted for, that's fine. But now it's on you to demonstrate that we've missed that. You
There's
can't
an
just say
optical
there has
variable.
to be something
What?
there that brings something
We
back to planet.
we see inside of a celestial sphere. I don't remember the exact steps for the argument, but there is a thing that you guys are just basically throwing out and disregarding.
What's that?
As I said, I'm not really sure of the argument. Hopefully, someone else will jump in who knows the celestial sphere, the sort of limits of optics of our eyes. This seems to be disregarded on the sort of globe model.
Yeah, the limits of optics of our eyes is at best angular resolution. Light doesn't stop working at a distance. We don't see things because light attenuates over distance. It attenuates due to distortion, obstruction, or diversion.
Yeah.
So light travels straight
And
indefinitely unless it's
I was kind of
obstructed
asking myself
or
the question before, right? Like if we exist inside of an electromagnetic field, which we do, and like gravity, which you attribute to the downward vector, is attributed to an electromagnetic field. Just like thinking, wouldn't the light as it courses horizontally through that field be pressed down, and that could just cause the bending of light itself? I don't know. Have you guys ever thought of anything like this?
it would very much depend on the mechanics of that electromagnetic field. Like there's an electromagnetic field, if you're talking about like the magnetic field of the Earth, maybe, but that's not going to do it. If you're saying that gravity is due to like electrostatics, I don't know if that would work in terms of bending light. But there's other reasons why we know that's not the case. Like gravity would work very, very differently if it were based on electrostatics.
Sure. Just a hypothesis for the second one. The first one still stands. I just don't know how to argue it.
Well, if someone can name the thing that we missed, I'm all too happy to hear the argument.
But you get what
I
I'm
got to make
saying,
some
though.
noise for a bit.
With standard
I do,
refraction.
but so it sounds like sorry, pardon me. It sounds like you're saying something is an excuse until it's been verified scientifically.
Yeah.
And as far as optics, I would say that we've very much done that. Newton was playing around with optics way back in the 1600s. And since then, we've learned a great deal more. Like all of these things that we've done in the lab are verifications of all the things we know about light and how light bends and how light travels and how things distort light and lenses and refractive indexes, et cetera, et cetera. Like we know these things.
Yeah, but when you're dealing with a chaotic atmos, right, with many gradient densities and evaporation and humidity and heat and particulates of pollen and dust, it's not, a controlled lab, dude. You know what I'm saying? Like it's not pristine or sanitized. You know what I'm saying? Like it's way too
I understand
chaotic
what you're saying.
for you to come up with some number. Now, granted, there's an average refraction every day. There's an average standard refraction. I'll give you that. But it just happens that the numbers that you came up with just are there to fix it, right? To make it fit the globe radius.
No, that's where I disagree with you. So it's true that there's a lot of things happening, that the world outside the lab is chaotic and and not as well controllable. But we can understand how humidity affects light. We can understand how temperature affects light, how density affects light. We can see the different ways that we can put those things together, and we can match that with what we're seeing out in the world. It's not just a post hoc rationalization, we're understanding how these things match what we already know about light. We can make approximations. There will be approximations unless we go out there and measure every molecule that's out there, but they're better and better approximations. And for those approximations to be so wrong that we've concocted a globe over instead of from flat Earth observation, like there's, it's just not possible they're that far off.
All right, man. Well, you said you were leaving, right?
Yeah, I'm
about to lose reception. So,
I can take over. Hello.
hey, Don, what's up? Good morning.